Hi everyone. So today we're going to pick up our study of confidence intervals. We're going to start on page 6 of your notes packets. So where we left off, we talked about the idea of a confidence interval and the fact that it's some kind of point estimate plus or minus a margin of error. Now sometimes a point estimate is a proportion, sometimes it's a mean, sometimes it's a median. But for today, we're going to be focusing on when our point estimate is a sample proportion, or in other words, p hat. So we have an example on page 6. This just kind of reviews what the last video talked about. According to a Gallup poll on August 13, 2010, the 95% confidence interval for the true proportion of Americans who approved of the job Barack Obama was doing as president was 0.44 plus or minus 0.03. You might hear this in a report like on news or on TV as 44% with a margin of error of 3%. And so that's just another way to report it. You might also see the confidence interval listed as parentheses. So we get this number by taking the 0.44 minus 0.03, and then we get 0.47, 0.44 plus 0.03. So we're adding and subtracting 0.03 to 0.44. You will also see it today, a confidence interval, as maybe a line, kind of like a number line. So the number line is trying to show you like, okay, well, here is the point estimate, the 44%. That's what we found in our sample. But then we're also going to calculate a margin of error in there. So we're going to estimate that the true proportion of Americans is somewhere between 41% and 47% who would approve of the job. And there are two things that you have to interpret with a confidence interval. One is the confidence interval interpretation. So that's what is saying, like, you find a confidence interval. All right, now tell me what that means. Here is how you would interpret this. We would say we are 95% confident that the true proportion of Americans who approve of the job Barack Obama was doing. And it's really nice to just pull that language straight from the problem. The true proportion of Americans who approved of the job Barack Obama is doing as president. Just kind of copy and paste that there. That's our population of interest. Was between 0.41 and 0.47. So if you're asked to interpret a confidence interval, that's how we'll interpret it. If instead we're asked to interpret the confidence level, the confidence level is the percentage. So here our confidence level is 95%. And so when you're asked to interpret just the confidence level, not the confidence interval, then you're being asked to say, okay, well, what does that 95% mean? Well, that means if we were to do this over and over and over, if we were to take many samples of the same size from the same population and create a brand new confidence interval, so keep calculating confidence intervals for each new sample, then 95% of those intervals that we calculate would have the actual true population proportion. So now today what we're going to focus on is this margin of error. How do we get that? Where does it come from? What all makes up those things? So now it's important to realize that when we are doing a confidence interval, we are trying to take some data from a sample and make an inference about the population. So when this poll was conducted, they could not, and in polls in general, whenever you're doing a poll, it's impossible to ask the entire population, hey, what do you think of the job that the president is doing? Do you approve of it or not? It's impossible to ask every single person in the entire population of the United States how they feel about that. So we take a sample and then we try to make a prediction based on that sample. So what this confidence interval is showing is that for the sample that they found, 44% of the people in that sample said that they approved of the job. So that is our p hat. P hat is 0.44. That's the point estimate. And then the 0.03 is a margin of error that we're adding to account for variability. Because what if we asked this specific sample and we got 44%? Great. But if I took a different sample of the same size, is it likely I'm going to get 44%? Probably not. But it should be pretty close based on this calculated confidence interval. So it is important to keep in mind that whenever we do calculate confidence intervals and we do use those to make inferences about populations, go look at page 7. Our calculation method is going to assume that our data is coming from a simple random sample of size n, so a specific size from the population of interest. And yes, we are adding and subtracting a margin of error, but the only reason we're adding and subtracting a margin of error is because it's just to cover variability due to sampling. In other words, chance variation. The fact that whenever you take one sample and calculate a proportion from a specific sample, you might get a different number if you were to take a different sample. And that's just differences from individual to individual. So we need to have a random sample. The margin of error is only accounting for variability that might happen from getting different results in each sample. The margin of error does not account for any source of bias, any source of systematic favoring of one outcome over another. So those are important to keep in mind. That being said, there's also some conditions we have to check before we can even calculate a confidence interval. Those conditions might look pretty familiar to you. Now, these conditions are specific to calculating a confidence interval for population proportions. So when we're working with P for our population proportion and our point estimate P hat. The first condition that needs to be met is called the large sample condition. And that requires that the sampling distribution, which is what we just talked about for sample proportions, must be approximately normal. And if you remember from last chapter, we had that n times p had to be greater than or equal to 10, and n times 1 minus p had to be greater than or equal to 10. But the problem is that we're trying to figure out what p is. We don't know p. We're trying to estimate it. So for this condition, instead of using p, we'll use the p hat number that we're given. So our sample data. So again, that's our sample proportion. The random condition, the sample has to come from either a simple random sampling, or if you're doing an experiment, there needs to be random assignment of treatments. So either a simple random sample or random assignment of treatments. And then the independence condition, if we're sampling without replacement, then we have to check the 10% condition, which says that your sample size needs to be less than or equal to 10% of the population size. That is, let me rewrite that. Now, note that you only check 10% condition if you're sampling without replacement. If you're doing an experiment, you do not need to check this 10% condition. So you might want to write yourself a note, and they're starting to not give credit when you check it when you're not supposed to now. So if you're doing an experiment, or sampling with replacement, we do not check 10%. Because if you're doing an experiment, then those treatments are independent of each other. If you're sampling with replacement, then you have independent samples. This is dealing with making sure that we have independence. And if you have a small sample relative to your population, then that will work. Okay, so now let's calculate our first confidence interval. We still have quite a bit of work to do, but let's get there. So we're going to skip ahead. We're going to go to page 9. And we're also going to need Desmos now, because we don't know how exactly to build our confidence interval, but we have enough information to use Desmos to calculate one. So we'll start there, and then we'll break down the pieces of the confidence intervals. So the example says a recent survey wanted to see what proportion of high school students believe there's life on Mars. The poll's population was all American high school students. They selected a simple random sample of 430 students. So I see that and I'm like, oh, sample size is 430. And found that 204 of them believe there is life on Mars. So 204 out of the 430. So that tells me the proportion in my sample is 204 out of 430. So then it says, construct and interpret a 96% confidence interval for the proportion of high school students who believe there is life on Mars. So notice there's quite a bit of space. There's some steps we're going to need to follow. The first step that we need to follow is the state step. That's where we're going to state what we're trying to estimate and with what confidence level. So if you look on the page before, we've got a state, plan, do, and conclude. So in the state part, what are we trying to estimate and what confidence level is that? So here we're going to write, we want to estimate P, not P hat. We have P hat. We want to estimate P, the population, which is the population proportion. And here I like to just use the wording from the problem. So it says construct and interpret a confidence interval for, and I just right here is like kind of copy and paste exactly what they say. The true population proportion of high school students who believe there's life on Mars. And then we also have to say the confidence level, which is 96%, with 96% confidence. So we would consider this section the state part of this open-ended problem. Okay. Then the plan, we have to identify the appropriate inference method, so the name of the confidence interval we're going to use. Then we're going to check the conditions. So in the plan part, we need to talk about the name of our confidence interval. So we'll say we will use, and the name of the type of confidence interval we're doing is a one sample, because we have one sample. Z interval, and we'll talk about why is a Z interval later, for proportions. So you do need to write all of that out because there's two samples, there's T intervals, we can do some for mean. So we're going to use that confidence interval method, and our conditions are the three conditions we just talked about. Not conditions, conditions. So the first one is the large sample. So I need to check that n times p hat is greater than or equal to 10, and also n times 1 minus p hat is also greater than or equal to 10. So let's see, if I take 430 and I multiply that by p hat, which is 204 over 430, is that greater than or equal to 10? Yes, it's 204. So yes, that's true. And then is 430 times 1 minus 204 over 430, not 1 minus. 1 minus that entire fraction. So I can do some calculations and I can say, okay, 1 minus 430 minus 204. Yes, that's definitely going to be greater than 10. There we go. So large sample condition is met. And so that tells us the sampling distribution of p hat is approximately normal. Our next condition is the random condition. So I'm pulling these from the conditions we just listed on page 7. So we got to check the random condition. The random condition, did we use a random sample? Yes, an SRS of 430 students was used. Okay, and then 3 is our independence condition. So are we sampling without replacement? Yes, we are, because we're talking to students and we're not putting students back and picking them again. So we are sampling without replacement. So we need to check, is our sample size is 204? No, our sample size is 430. So is 430 less than or equal to 10% of our entire population? And our entire population is all high school students in America. And we're going to say yes. We can assume that's a safe assumption. Check. Okay, so we checked our conditions. Third step. That's where the fun part begins. If our conditions are met, then we can construct a confidence interval. So if conditions are met, construct the confidence interval, write down the formula. We'll get into the formula a bit later. We're going to use Desmos first, and then we'll do the formula. So now we're going to use Desmos to calculate our confidence interval. So let me pull up Desmos. We'll do a side-by-side here. Put Desmos here. Split screen it. Pull the okay, so I can see the problem. You can see Desmos. We're going to go to inference. Notice we usually click probability distribution. We're not going to do that today. We're looking at inference, where we can use a sample data to make an inference for a population. Now notice we're doing proportion, so that's not quantitative. We're in categorical data. We're going to do a z-test for proportion. So we're going to click that one. And we have one sample. So ask for successes. That's asking how many successes that there were. So since there were 204 of the students who said they believed in Mars, I would put 204 here. And my sample size was 430. Okay, so we're going to create the test. So it shows z-prop test. That means a z interval, one sample z interval for proportions. We're going to click on confidence interval, and we need to, right here, type in what kind of percent that we want. So it says 96%, so 0.96 is what we type in. And oh my gosh, look, it gives me the confidence interval right there. So our one, draw. So our one proportion Z interval, or one sample, for P is 0.425 to 0.524. With our point estimate being right in between, which is 47.4%, which is that 204 right there. Okay, and so if you notice in the do part, write down the formula you use. You can write down the formula or the name of the test. So that's what we were doing when we were writing down one proportion Z interval for show values you substituted by an or on the calculator. So what we did in the calculator is fine. So what we wrote down is fine. Then we have to conclude. So we have to interpret. That's that construct and interpret part. So here's where that skill of interpreting a confidence interval comes into play. So grab my, for the conclude part, we can write we are 96% confident the true interval, no, that's not the true interval, the true proportion. And again, this is a great time to go back up to the original problem and then copy and paste this wording right here. The true proportion of high school students who believe in life, who believe there's life on Mars, is between 0.425 and 0.524. So 96% confident. So we're going to estimate it's somewhere between 42.5% and 52.4% of the high school students who believe there's life on Mars. So that's how I use Desmos to calculate a confidence interval. So a couple of the features on Desmos makes the confidence interval really nice. You can just type in whatever percentage of confidence that you want. Notice if I choose a large confidence value, so 99% confidence, I get a pretty wide interval. But if I type in I want to be like 10% confidence, I have a very small interval. So what we're going to talk about next is why that is. Why is a 99% confidence interval so wide versus so small, so like 25%. We will do significance test in the next lesson. So you're going to go to page look back at page 5. So remember this guy, it's kind of small on your paper, but it is the normal curve. That 68, 95, 99% rule. So do you remember that if I have a normal curve, again this was page 5, the mean is in the middle, and the middle approximately 68% of the data points fall within one standard deviation, and 95% fall within 2 standard deviations, and 99.7 fall within 3 standard deviations. Those percentages are where we're getting our confidence levels from. So if we want to be 95% confident, then we're roughly adding, we're taking our point estimate and we're roughly adding 2 standard deviations to that. So there's a formula we have to follow for calculating a confidence interval or constructing one. So now look at page 7, constructing a confidence interval for proportions. So right now we know that confidence intervals are the point estimate plus or minus the margin of error. And until this point, the margin of error has kind of been calculated, taken care of for you. But we need to understand what those components are that create the margin of error. So we'll have our statistic, and when we're working with statistics, it's that p hat value from the sample, plus or minus, and then we have this critical value called z star, times the standard deviation of the statistic, but most recently it's been referred to as the standard error. And it's called standard error because instead of using p to calculate the standard deviation, we have to use p hat. So it's called a standard error of the statistic. And that formula is the square root of p hat times 1 minus p hat all over n. So I'm going to point you to the formula sheet so that so you can know where those things are. If I can get to the right tab. So on the formula sheet, we've had for population proportions. In the last chapter, you worked, well, I lost it. There we go. In the last chapter, you worked with the mean of p hat being p, standard deviation of p hat being p, square root of p, 1 minus p over n. Now, since we don't know p, we're trying to estimate it, we'll use the standard error. So this is where you'll find that formula for standard error. Also notice the formula sheet does not have confidence interval formulas on it, but it does have a format, which is what we're looking at right now. Statistic plus or minus critical value times the standard error of the statistic. So you have to know, okay, well, I'm working with p hat, so I need b p hat. I got to find the formula for p hat, and then z star we'll figure out in a little bit. So back to where we were. On, I think it was page 7. No, yeah, on page 7. So here's that formula. Now the margin of error is made up of z star times the standard error of the statistic. So that's where we're calculating that margin of error for you. That's been calculated already. If you think about the normal curve and how you have the mean in the middle, and how much we're adding to get to each standard deviation. So like plus 1 standard deviation, plus 2 standard deviations, and so on. This is essentially the formula for a standard deviation. We're calling it standard error, but it's like calculating what that specific standard deviation is going to be. And then z star is how many, or the number of standard deviations you're going to add or subtract. So z star is like, oh, I'm going to add 2 standard deviations. I'm going to take my point estimate p hat, and I'm going to add standard deviations and subtract z number of standard deviations. So that's where z is coming from. Z star is referred to as your critical number, critical value, and then we've got our formula for standard of error. Properties, we've got a formula for margin of error. User chooses the confidence error. Our goal for to get a smaller margin of error, because we want to have accurate predictions, there's 2 ways we can do that. The first way we've seen is that we can decrease the confidence level. Or you can also increase your sample size to make a smaller, larger margin of error. Because if you increase this number right here, then you're dividing by a larger number, and so your margin of error is going to be smaller. Okay, so let's talk about the components of a confidence interval. First of one we want to talk about is that critical value. So the critical value is the z-score that sets the boundary on the confidence interval. It's asking how many standard deviations on either side do we want to go. And so when we calculated our confidence interval on Desmos, it took the z-score, not the z-score, the z-star into the account, but sometimes you've got to calculate your own critical value. So we need to know how to do that. So the way that we're going to do that is we're going to remember the standard normal curve. Okay, and the standard normal curve is the one that has the mean of 0 in the middle, and then the standard deviation is equal to 1. So it's normal, and then mean is 0, standard deviation is 1. Okay, this would be 1, 2, 3, -1, -2, -3. Okay, and all of these are referred to as the z-scores at the bottom. Okay, so if I want 80% confidence, then I'm going to use that standard normal curve and find the boundary points, like the numbers at the bottom, where approximately 80% of the values are. So that middle area would be 80%. That's what I've got to calculate. So if I draw a curve over here to calculate what I'm looking for, mean 0, standard deviation is 1. So I want to find these numbers. What are the boundaries where I have 80% in the middle? And I can do that with my standard normal curve on Desmos. So I'll pull up Desmos. Going to add inference. Now I do want a probability distribution at normal, mean 0, standard deviation of 1, create the distribution. I want the one with the cumulative probability where the inner area is 0.8 because I want 80% confidence. So I see it's bounded by -1.282 and positive 1.282. So I give the positive value for that z-star number. So here, when I'm doing 80% confidence, z-star would be 1.282. For 90% confidence, go back. Now I'm going to change that middle area from 80% to 90%, and I've got 1.645 for my new z-star value. So try 95% and 99% confidence as well, and then check to see, do you get about 1.96, and do you get approximately 2.576? So now if I come back to the example on page 9, page 9 is where we use Desmos to calculate our confidence interval, but if we want to use the formula to calculate it, the p-hat plus or minus z-star with the standard error of p-hat, then I would take what I know and plug stuff in with, now that I can calculate the z-star. So the p-hat would still be the 204 out of the 430 total, plus or minus. Now I've got to get z-star calculated for 96% confidence interval. So I need to go back to my normal curve, calculate z-star when that area is 96%, and it looks like it's 2.054. And then times the square root of, I'll plug p-hat in again, 204 over 430, times 1 minus 204 over 430, and then all over the sample size, 430. And if you calculate this number by hand, double check, you should get the same thing that we got with our decimals. So it is important to realize how to do both methods. and also realize where our margin of error is coming from, because you're not just going to be asked to calculate a confidence interval. You also have to be able to think about the parts of the margin of error. If I adjust z star, what would happen? What value of z star is going to give me a certain margin of error? If I adjust the sample size, what happens to the margin of error? So it's important you can do both ways. The other thing you'll have to do is figure out what sample size you need for a certain margin of error. So a lot of the times you're trying to do research and you need to figure out, okay, well, how many people do I need to ask in order for this research to be valid? So oftentimes researchers need to both limit the margin of error to a fixed amount and still maintain a certain confidence level. So to determine what sample size you need for a specific margin of error, we're going to look at the components of the margin of error. So margin of error is the second part of that formula. It's z star times the square root of p hat, 1 minus p hat, all over n for proportions. And if we need to maintain a fixed confidence level, then that means the z star can't be changed. P hat can't be changed, but what can be changed is our margin of error. So we can solve that for n. Since we're trying to figure out how many people we're going to ask, we won't know p hat until we actually conduct the study. So that's a problem because we're trying to calculate n when we don't know p hat, and then that's two unsolved variables. So we have two options. We can either use p hat value based on previous studies, or we can use a conservative approach and just substitute in 0.5, like giving a 50-50 chance. This one is more common for the work that we do in this class. So here's an example. Before conducting a nationwide polling prior to a national election, most good companies will decide ahead of time how many people to include in the poll based on a particular margin of error and confidence level. So let's say the Gallup poll wants to conduct a poll to see what proportion of voters would vote for Trump again if Trump were running for president against Elizabeth Warren. The Gallup poll wants to be 95% confident, so 95% confident is going to translate to a z-score, not a z-score, a z-star value of, go back to my normal curve, where are you, Desmos? 95% confident, z-star 1.96. So we're going to ask how many people do we need to ask in order to maintain a margin of error of no more than 3 percentage points. So I want margin of error to be less than or equal to 3 percentage points, which is 0.03. Okay, well, I know my formula for margin of error is the z star times that square root p hat 1 minus p hat over n. So I'm going to substitute everything I know. I'm going to take this expression that I need and substitute in the formula for margin of error. So substitute in formula, we have z star times the square root of p hat 1 minus p hat over n needs to be less than or equal to 0.03. We calculated z star, we know that's 1.96. We're going to use a conservative approach since we don't have any previous studies. So we'll say p hat is 0.5. So 0.5 times 0.5 over n. And now we have an algebra problem where we're solving for n. So I'm going to grab a calculator to help me do this side by side. I can, let's see, I need to get the n by itself, so I'm going to divide both sides by 1.96, so 0.03, divided by 1.96. And then I will have this, the square root, let's see, 0.5 times 0.5 is 0.25. So square root of 0.25 over n needs to be less than or equal to 0.015306. And I'll just stop the 306 right there. 15. 306. Okay, now I need to get out that radical gone so I can square both sides. When I square on the left side, the radical cancels out and I'm just left with 0.25 over n, less than or equal to. Now I need to square this decimal, so I'll just copy it. Actually, I'm just going to go here, highlight this, and I'll square that. So 0.00002342. Okay, so now I got to get the n out of the denominator. I can multiply both sides by n. So multiply by n over here, multiply by n over there. I'm running out of space. So I'm going to come over here. We get 0.25 needs to be less than or equal to that number times n. So it looks like I need to divide both sides by that 0.00234 So I'll take 0.25 divided by that. See if I can copy and paste this into the denominator. There we go. And so if I divide, then I have 10677. Nope, 7, just 17. 0.11. It's less than or equal to n. So in other words, n needs to be greater than or equal to 1067.1. And since we're talking about a sample size, how many people do we need to ask? We need to ask at least 1,068. At least. People. Always round up. Even though we have 0.1, we're talking about people here. So we can't ask 0.1 of a person. All right. That concludes Notes 1. If you're still here, your homework packet did not have a title on homework 3. So homework 1, you need to finish all the problems until you get to page 1 through 3. So homework 1 is pages 1 through 3. And you'll see on page 4 that homework 2 starts again with page 1. So homework 2 is page 4. So this is what you need to do. Homework number 1 on pages 1 through 3. Finish it up. All right, have a great day, and I will see you guys again soon.